Right, here we go. Here's the walkthrough of Specimen exam paper for component 1, the Eduqas syllabus, the one that you just did in class. Right, the very first question, it was a calculation question. If you're looking at it again, it gives you a lovely graph. It tells you calculate the rate of uptake of carbon dioxide between 250 and 750 lux. Yes, the first thing you're going to see is that you're going to have horrendous looking units, and then the horrendous looking unit times 100, and your answer needs to be in that horrendous looking unit, when actually it is how many moles per centimeters squared per minute per lux per intensity of light, that is. Don't let that confuse you too much. The key thing to spot here is that you've got a times 100 factor here that you might overlook. So how did you again calculate a rate? It's that y over x, the change in y over change over x, change in x. So let's have a look from 250 to 750. So from 250 to 750. And the other thing that is a bit awkward for you to see is actually the scale here on the x-axis. If you're counting your scale properly, you will spot that every small grid is actually 5. So uptake of carbon dioxide in 5, whatever that long unit is. Okay. So first of all, you have got here, what change over x would that be? That is 500, the difference between 750 and 250. Then how far do you get up and get across for both these values? And you will get, hold on a second, I'm not doing that properly on the line. You will get to 155, and you will get to 65 here. If I didn't do that right either. The mark scheme gives me 65 here. Okay, so step 1 is identifying your y-axis, and then to calculate that difference gives you the 155 minus 65, which should give you 90. So you've now got your change in y over change in x. So your next step is your change in y over change in x. That, as per calculator, gives you 0.18. Now, 0.18, hold on a second. This is now basically your rate of uptake. However, because it's hard to display it on the graph the way it is, they've decided, hold on a second, the numbers are too small. Let's just times it by a factor of 100 to make it look like something nice and easily plottable. So for you to now get into that without the factor 100, because that's what's expected from you at the end, you now need to divide this by 100. So divide by 100. That would give you 0.0018. Now it also nice and sneakily tells you do that here in standard form. You should already see that we're doing to the power of minus, 10 to the power of minus something. Standard form, you can do 1.8, or you can actually round it straight to 2. So that would be 2 times 10 to the power of minus 3 rather than 0.18. The mark scheme is giving you, that is 2 times 10 to the power of minus 3. So that would be rounded. Why are you rounding? You have not got very precise units here. Okay, so that is a question of precision here. The mark scheme, please feel free to just pause the video every now and then, as and when I'm holding the mark scheme up, just pause it right there and then if you want to have it in front of you. The next question here, explain the difference in the rate of uptake of carbon dioxide between parts A and parts B. Please, it says explain. It doesn't say describe. So beautifully, if you're telling me nicely, yeah, A increases and then starts to level off, and yeah, and B has finally plateaued somehow. That is a description. It is asking you to explain why do we get a situation where as light intensity increases, as the plant gets more and more and more light, it absorbs and takes up more and more and more carbon dioxide. This question is a question on limiting factors. What is actually stopping the photosynthesis at that point? Here, because if you increase light, you get obviously more photosynthesis happening or more carbon dioxide being taken in. That means during phase A, you have got light as the limiting factor. However, in phase B, you can give it more and more and more light. It still does not increase in activity. Some people said that the chlorophyll got bleached and therefore the plant no longer takes up carbon dioxide. Hold on a second, then your graph should be doing something like that, which it clearly doesn't. So the graph has plateaued and it stays high, which means the light intensity is fine, but something else at this point is missing. Could it potentially be temperature? Yes, it could, but the question paper tells you that it's at a lovely 15 degrees. So what has to be the limiting factor here is carbon dioxide. That's simply for that second part. For B, you've got carbon dioxide limiting. So B, carbon dioxide is limiting factor. And for the part A, light is limiting. Let me just go over to the mark scheme here. Oh, you can't see that. Mark scheme here, if you wanted to see it as the mark scheme version. So carbon dioxide is in excess, therefore light intensity is increasing. Therefore, so as the light intensity increases, so does the rate of uptake. Right, I wrote that wrong. Light is not limiting, did I? I don't write that wrong at all. Yeah, right, light is limiting and as it increases. So that's right. So does CO2 uptake. Okay, I probably said it right and then didn't write it down right. Or maybe I said it wrong as well. Okay, moving on to the second page here, which is still question 1. So you've got below a light intensity of 50 lux. Photosynthesis takes place even though there's no uptake of our carbon dioxide. So it tells you photosynthesis takes place. So don't tell me in your answer photosynthesis has stopped, because it tells you photosynthesis still happens. However, no more carbon dioxide is taken up. So hold on a second. Where does then what happens? What else is missing there? This question is asking you to think of 2 parts. It's telling you, but it doesn't tell you that you need to consider respiration. This is the compensation point question. This is saying that, hold on a second, the plant will produce its own sugars. It will produce its own trioses, which then get transferred into whatever else. But then it does respiration and it uses up those sugars it has made itself as well. So the respiration rate below the 50 lux light intensity, the respiration rate has to be either higher or the same as photosynthesis. So at exactly 50 lux, where you've got no more uptake, would be the compensation point. Below that, carbon dioxide is is produced by respiration at a faster rate than photosynthesis can compensate for that. So if you're looking at C on the mark scheme here, below the 50 lux, respiration must be higher than the rate of photosynthesis, and at the compensation point, which seems to be 50 lux, the respiration rate and photosynthesis rate are equaling. This would have been the 2 marks for that one. Then looking at D, and they will give you questions where they're giving you some fancy new thing, some fancy new compound or new name. In this case, it's giving you a weed killer. It tells you the weed killer only blocks electron flow from photosystem 2. What you need to have in your head is literally that Z scheme of what photosynthesis was, where you've got the hydrolysis of water here at photosystem 2, and here would be photosystem 1. And part of your head should maybe go that here we have got that the cyclic path, and the non-cyclic would lead here to NADP being reduced. So what is actually happening? The electrons that should flow here, these electrons here, they can no longer flow, because that is here what that weed killer stops, that path. It clearly tells you that the non-cyclic is still working. Why? Because actually you're not interfering with that cyclic path at all. It blocks the electrons from earlier. So the photolysis of water, the hydrolysis here, the photolysis will no longer happen because you cannot take up that electron, which means altogether the transfer, as it says, transfer of electrons from photosystem 1 means that altogether you're not producing an ADP, you're not producing the ATP you're supposed to produce, you're producing far less, you're producing the little bit of ATP here, because remember here you've got still the electron transport chain along here. So you're having some ATP made, but it is not sufficient. You're having this ATP made, you're not having this, and you're not having this ATP made. So describe, let's have a look at the mark scheme. It stops the electron flow from photosystem 2 to photosystem 1. It's blocking that reduction, so no NADPH is made, no photolysers of water. The cyclic isn't stopped because the electrons pass straight away from photosystem 1 back to photosystem 1. I probably have been a bit nice on marking this one here, so maybe some people have actually got a mark there for that last bit when you shouldn't have. Last one for question 1. I need to stick to the 15 minutes limit because otherwise YouTube is going to be grumpy with me. Explain why a plant would die when the weed killer is sprayed onto it. So you have here, from here you have got less ATP, and you've got literally no NADPH being made, okay? No energy carriers, so no ATP and no reduced NADP. So we have got a problem where what cannot work? Where are those substances meant to go? They're meant to go to the Calvin cycle. The Calvin cycle cannot do its thing without the energy carriers actually supplying that Calvin cycle, which means if the Calvin cycle no longer works, we're not getting any triosis, we're not getting any sugar, we're not getting glucose, fructose, whatever you want to call it. Therefore, we cannot do respiration. So no sugar is being made, therefore no respiration, and therefore the plant actually ends up pretty much dead because it can't do respiration. Nothing functions on it. Looking at the mark scheme one last time for question 1. Cannot generate an ADPH, less ATP, Calvin cycle stops. Therefore, all those sinks will not have any of the sugars for respiration.